Good morning, good afternoon, and good evening, depending on where you are in the world. First, welcome to SIGIR 2020. It is my great pleasure and honor to introduce our first keynote speaker, Professor Geoffrey Hinton. I believe everybody knows Professor Hinton. He is a Turing Award winner, the most cited computer scientist, and is considered as the godfather of deep learning. Professor Hinton received his PhD in artificial intelligence from University of Edinburgh in 1978. After 5 years as a faculty member at CMU, he became a fellow of the Canadian Institute for Advanced Research, and then moved to the Department of Computer Science at University of Toronto, where he is now an emeritus distinguished professor. He is also vice president and engineering fellow at Google and chief scientific advisor of Vector Institute. The first time I got to know Professor Hinton was through Karen Spark-Jones, where I studied for my PhD in the United Kingdom in 1990s. Professor Hinton is internationally distinguished for his work on deep learning. He was one of the researchers who introduced the backpropagation algorithm, and then the first to use backpropagation for learning word embedding. His other contributions to neural network research include Boltzmann machines, distributed representation, time delay neural net, mixture of expert, variation learning, and deep learning. Together with Jan LeCun and Joshua Bengio, Professor Hinton won the 2018 Turing Award for conceptual and engineering breakthroughs that have made deep neural network a critical component of computing. In 2018, he was awarded a Companion of the Order of Canada. Finally, let's warmly welcome Professor Hinton.
Okay, thank you very much for that generous introduction, and welcome to the conference. I'm going to talk about the future of neural networks, but in order to do that, I'm going to talk quite a lot about the past of neural networks. In particular, I'm going to talk about unsupervised learning. So there's various types of learning tasks. The most obvious is supervised learning, where you learn to predict an output when given an input vector. There's reinforcement learning, where you learn to select an action, like which move to play at Go. And then there's unsupervised learning, where the aim is to discover good internal representations of the input. It's much harder to define this mathematically, what you mean by a good representation. First of all, I'm going to explain why I believe we need unsupervised learning. If you look at people, which is after all what we're trying to compete with, we have about 10 to the 14 synapses, and we only live for about 10 to the 9 seconds. So that means explicit labels or payoffs can't possibly provide enough information to train all those synapses. We have about 10 to the 5 synapses per second. Now, there's some arguments against the idea that we learn all those synapses. One argument is, what if they're innate rather than learned? Well, it's hard to see how they could be innate. That's appealing to evolution, and evolution is a much less efficient algorithm than backpropagation. What if they're highly redundant? Well, we pay a big cost for having a large brain. In particular, women pay a big cost for us having a large brain, and so it's very unlikely that we're wasting capacity. We operate in the regime of huge models trained on not much data. That's very unlike conventional statistics. For us, experience is expensive and synapses are cheap, so we need to look at learning algorithms that can use not much experience and a lot of parameters. If you look at the objective functions people have used for unsupervised learning, there's maximum likelihood, which is the obvious one. And that means adjusting the parameters of a generative model to maximize the probability that the model would generate the observed data. A simple example of that is fitting a mixture of Gaussians to a data distribution, where you try and find the means and variances and mixing proportions of the Gaussians, So that if you pick one of the Gaussians according to the mixing proportions, and then generate a point from that Gaussian, you're as likely as possible to generate things that look like the data. Then there's autoencoders, which aren't exactly maximum likelihood. And what they're trying to do is find an economical representation that allows the data to be reconstructed. And then there's one I'm going to talk about a lot in the second half of this talk, which is spatial or temporal coherence. And the idea is to extract properties that are coherent across space or time. And this is definitely different from maximum likelihood learning. So let's start with autoencoders. Autoencoders are a way of using a supervised learning algorithm to implement unsupervised learning. So we have a network in which data comes in at the bottom, and the output of the network is a reconstruction. And the aim of learning is to make the reconstruction be the same as the data. The network has an encoder, which takes the data and converts it into a code vector. Often you'd like that code vector to be small, or sometimes you'd like it to be a vector that's probable under some prior distribution. And then we have a decoder that takes the code vector and tries to reconstruct the data. So the decoder is a conditional generative model. It's given the code vector, and then it tries to generate data that looks like the real data. For about 20 years, people thought that it was very difficult to train deep autoencoders. So the idea was around from the beginning of the popularity of backpropagation in the mid-1980s, but nobody could get it to work in deep networks. And the question is why? Well, we were using the wrong type of neuron. We were using sigmoid units or tanh units rather than rectified linear units, which are much easier to train in deep nets. We also initialized the weights badly. It's very important if you want to train a deep net to scale the weights when you initialize them, so the backpropagated gradients don't explode or vanish. But also computers were slow. They weren't quite slow enough to excuse the fact that we couldn't get them to work, but they were slow nevertheless. In 2006, Ruslan Salakutinov and I introduced a way of training deep autoencoders. And it was a very simple way to train them. And it involved stacking up a bunch of shallow autoencoders. So you start by training a shallow autoencoder that takes the data as input. It has a hidden layer of feature detectors, which you can think of as a code layer initially. And it tries to learn feature detectors that allow it to reconstruct the data. Once it's done that, you take the activities of the feature detectors and you treat them as data, and you do it again. And once it's done that, you do it again, and you can do it for as many times as you like. And so without using any labels, this will pre-train lots of layers of feature detectors. This is called unsupervised pre-training. So each new autoencoder is treating the activities of the feature detectors you've already learned as its data, and it's learning to encode them further. Now, the interesting thing about the algorithm we came up with was, first of all, that it revived deep learning in 2006. People then started training deep nets. It had some interesting math. If the shallow autoencoders are things called restricted Boltzmann machines, then there's some math showing that every time you add a new shallow autoencoder to the stack, you get a new variational bound on the log probability of your model generating the data, and that variational bound is better than the previous variational bound. As with much fancy math, it's completely irrelevant in practice, but it's very good for selling the idea. Since then, people have developed more sophisticated kinds of deep autoencoder. In a greedily learned stack of shallow autoencoders, there's no pressure for the feature detectors you extract early on to be the feature detectors you're really going to need for representations you're going to extract later on. To overcome this problem, we can learn a deep autoencoder end to end. That's what people had always tried in the past, and it never worked because we were using the wrong kinds of units and not initializing it properly. But with faster computing and better units, that now works very well. It may be a problem for biology to do that, but for computers, it's not a problem. And there've recently been major advances in learning deep autoencoders. So in 2013, Welling and Kingma introduced variational autoencoders. And the idea of these is you'll have an encoder, shown on the left there, that takes data and converts it into a real valued code vector. And then you have a decoder that takes the real valued code vector and reconstructs the data. And the aim of the encoder is twofold. It wants to find a code that can maximize the probability of that code under a prior distribution. So the idea is in that real value code space, you have a prior distribution, which is normally a Gaussian, and the encoder is trying to find codes near the mean of that Gaussian, codes that are probable under the Gaussian. But it's also trying to find codes that will allow it to reconstruct the data. The decoder takes the code and tries to reconstruct the data accurately. And it does that using a variational approximation that I'm not going to go into. But by using a clever mathematical trick, Welling and Kingma were able to get all the derivatives they need to train a variational autoencoder, both to have a high probability of reconstructing the data from the code and to produce codes that themselves have a high probability under the prior. I'm not going to talk more about variational autoencoders, but they're currently one of the best methods of doing unsupervised learning. I will talk more about a method called BERT. So BERT is a deep autoencoder that's trained to fill in missing words in a sentence. It's actually very relevant to information retrieval because BERT extracts extremely good representations of words, and those should be very good for understanding documents. And as we'll see, they're certainly very good for building a model of what's in documents. So in BERT, you have many layers, and in every layer, you have an embedding of each of the input words. So when a word comes in, it's converted into a vector, and you'll have that vector representation of a word in the first hidden layer. Then in the second hidden layer, you'll have a better vector representation of that word, and the representations of the words of a given word will get better as you go through the network. In fact, the representation in layer L+1 is learned, and it's produced by comparing the embedding of that word in layer L with the embeddings of the other words in the sentence of layer L. And those comparisons are done by a complicated form of attention called a transformer, which I'll now try and explain. It's a very clever idea. And the embedding of the words you get just before the network tries to output the words, which includes, of course, filling in words that were missing, that final embedding turns out to be a very good representation of words to use for things like modeling the content of sentences and for many different natural language tasks. And I'll show you one thing it's been used for where it works extremely well. So if you have a standard one-dimensional convolutional neural network for representing strings of words, at one level, you'll have these vectors that represent the words in the sentence, and you'll get a vector to represent those words at the next level up by combining information via weight matrices from the words at the level below. So you simply look at all the words that are nearby you in the level below, and you combine those representations into a better representation of your word at the next level up. BERT does the same thing, but with attention. So BERT looks like this. In order to combine the representations of the words at the bottom level there, to make a new representation of the word in that particular column at the higher level, we're going to use something that actually looks a bit like information retrieval. Each word, via some learned weight matrix, is going to produce a query vector, a key vector, and a value vector. And then for each word at level L, you're going to take its query vector and you're going to compare it with the key vectors of all the other words. And when you find a good match between the query vector and the key vector, when the exponential of that product, that scalar product of the query vector and the key vector is big, then you're going to allow the value vector at that nearby location to influence your representation in the next level up. So for example, if I'm the word June, and I'll produce a query vector, and the query vector will be good at matching the names of months, but it'll also be good at matching women's names, at least in English. And so it will select relevant words in the rest of the sentence and use those relevant words to modify the representation of June. If there's several other women's names in the sentence, the representation will become more like the representation of a woman's name. And if there's several other months in the sentence, it'll become more like the representation of a month. So it'll be refined by the context. So this is like information retrieval, except that the queries and values and keys are all learned, and they're all learned by backpropagation, the error that it makes in filling in missing words. So you can use this kind of neural net for language modeling. What you do is you first pre-train word fragment embeddings using transformers. That is, you take sentences, or actually pieces of text quite a lot longer than sentences, thousands of fragments long, and you put them through many levels of this autoencoder, which is learning all these keys and values and queries, so that the word representations get refined, and just before the output, you get representations that have been refined very carefully by lots of context. And so they're very good representations of those input word fragments. Then what you do is you use those representations of word fragments in another neural net, and this other neural net is trained to predict the next word fragment from many previous word fragments. So it's an autoregressive model that looks at previous word fragments and tries to predict the next word fragment. But it doesn't look at the raw word fragments, it looks at the representations of those word fragments produced by BERT. And they're going to work much better than the raw word fragments. After training this language model, you can see what it believes, or you can see how much it understands by giving it an initial word sequence and getting it to predict the probability distribution for the next fragment. So the way you do that is you give it a context, it predicts the probability distribution for the next word fragment, and then if you want to generate from the model, you just pick from that distribution. So if it says the probability, there's a probability of 0.5 that the word the comes next, then with probability 0.5, you pick the word the. And then you tell the network, actually the correct word was the, what do you think comes after that? And it'll give you a new probability distribution for the next word. For example, it might say there's a probability of 0.1 that it's cat. And so you pick from that new distribution, and with a probability of 0.1, you pick the word cat. So if you pick the word cat, you say to it, okay, the next word was cat. What do you think comes next? And so you can play this game where you get it to guess a distribution for what comes next. You pick from that distribution, you tell it it was right, and then you say, okay, what comes next? And that way you can get it to produce long strings of words. And it's amazing what it produces. And you can keep going until, for example, you get to a full stop, or you can keep going even after a full stop. You can keep going for as long as you like. So what I'm going to show you now is if you take BERT and you train it on billions of words of text, and then you take the embeddings produced by BERT, a very big version of BERT, and you train a language model that has 175 billion parameters on this very big set of text. And that training took over 1,000 petaflop days. Okay, that's a long time. 1,000 petaflop days is an amount of computation that was inconceivable until quite recently. And so once you've done that, you can get it, for example, to generate news articles. You can get it to generate all sorts of things. It knows about all sorts of things. But let's just focus on one particularly nice example. It was given the beginning of a news article. So it was told the title is United Methodists Agree to Historic Split. The subtitle is Those Who Oppose Gay Marriage Will Form Their Own Denomination. And then the article is, and now it has to start producing words. And it produces them one word fragment at a time. And each time it guesses a word fragment or gives you a distribution, you pick from the distribution, you tell it was right, and you say, okay, what's the next word fragment? And here's what it produces. Now, this is cherry-picked. This is one of the best examples from this great big GPT-3. But what's interesting is most people are unable to decide whether that's a genuine news article or it was made up by BERT. It kind of passes the Turing test. It's full of lots and lots of common sense. Notice that linguistically, it only uses words. It's perfectly capable of generating non-words, but it doesn't. It knows how to use quotes. It has coherence, that is, sentences that come later on refer back to earlier sentences. The whole thing makes a lot of sense. So this is just an example of what can now be done by first training with unsupervised learning using BERT, and then training a huge language model. It's the only really impressive example I'm going to give. I'm going to now go back to the underlying ideas about how do we do unsupervised learning. So variational autoencoders and BERT are better than the greedily stacked autoencoders that Ruslan Salakutinov and I introduced. And it's because the end-to-end learning ensures that the hidden units in earlier layers learn to extract features that are needed by later layers. That's what backpropagation is good at. And I believe the brain must have a way of adapting the feature detectors in earlier layers so they extract what's needed by the feature detectors in later layers. Stacked autoencoders that learn greedily don't have any incentive to do that. When they're learning the early feature detectors, they're not taking into consideration representations at later layers, because those representations haven't been learned yet. You can fine-tune them later on to do that, but in the unsupervised learning, they don't do that. So the question is, can we fix this? And one question is, does the fix really require backpropagation through multiple layers? For the last few years, I've been very keen to find a way of doing unsupervised learning in deep nets that doesn't require backpropagation through multiple layers, because I don't believe that's what the brain does. I've tried very hard to come up with ways the brain might do it and invented some fairly complicated schemes with other people, but I don't really believe the brain is backpropagating through many layers. So here's an obvious fix. And most of the rest of this talk is going to be about why this obvious fix doesn't work and how the obvious fix can be refined so that it does work. And the obvious fix is to learn each layer of features so that they're good at reconstructing what's in the layer below, but also they're easy for the layer above to reconstruct. So we're just going to consider the layer below and the layer above. It means we're going to have to learn all the layers at the same time. And we're going to try and make features which are good at reconstructing the layer below. That's the greedy autoencoder objective function, but are also easy for the layer above to reconstruct. That is, they fit in with what the layer above would naturally predict. This has a very pleasing interpretation. The layer above is going to make a top-down prediction, and that top-down prediction is going to supervise the learning of the bottom-up connections. The bottom-up connections are going to produce a representation, and that representation is going to act as a target for the top-down prediction. So what's produced bottom-up is acting as a target for learning top-down predictions, and the top-down predictions are acting as a target for learning what to produce bottom-up. Bottom-up and top-down are supervising each other. So let me show you an example of that, of using contextual agreement as a teacher. If you consider a sentence like, "She scrommed him with the frying pan." Hopefully you've never heard the word scrom before. You suspect it's a verb because of where it is in the sentence and the ending on it, but you have no idea what it means initially. But after you've seen that one sentence, most people have a pretty good idea of what it means. It means something like, she hit him over the head with the frying pan. Now, maybe that's just the Western culture I live in, where people do things like that. But you get a pretty good sense of the meaning of a word from a single sentence. You don't need thousands of examples. And that's what's appealing about using top-down predictions as teachers for what you extract bottom-up. You can learn from one or a few examples. The same thing happens in vision. A more global context predicts what you should see in part of the image, and that top-down prediction allows you to train your neural net to extract what you should be seeing there. So, for many years, I've been trying to train stacks of shallow autoencoders in this way. I return to it about once every 5 years, and it's just recently started working. The reason it doesn't work easily is because you can easily make a top-down prediction agree with what you extract bottom-up by making both of them be 0. So the objective function that says make top-down predictions and things you extract bottom-up agree is not a very good objective function. It causes things to spiral in towards 0. The bottom-up predictions will always, the bottom-up extractions will always undershoot the top-down predictions. That's the best way to minimize the squared error if you're not sure. You try, or a cross-entropy error. You undershoot the things you're trying to predict. But the top-down predictions will also try and undershoot the bottom-up extractions. So you get these two representations, each is learning to undershoot the other, and it's a death spiral that just spirals into them being 0. Now, a long time ago, I came up with a way of avoiding that with one of my students by using a better definition of what it means for two things to agree. Instead of saying they should be equal, you say they should be similar relative to how much they vary over different training cases. So on a particular training case, you'd like the bottom-up prediction in one part of a neural net to agree with the top-down prediction, the thing you extract bottom-up to agree with the top-down prediction from the layer above. But you'd like it to disagree with the top-down predictions on other cases, on other training cases. In other words, you don't want it to be a trivial agreement. You want it to be an agreement that's specific to that case. So I'll return to that way of training stacks of shallow autoencoders after I've discussed a different way of doing unsupervised learning. So this is a radical alternative to both autoencoders and generative models. Instead of trying to explain every detail of the sensory input, we're just going to focus on extracting properties that are spatially or temporally coherent. Unlike autoencoders, that allows us to ignore noise. If there's some pixels that are pure noise, they're of no real interest. If you're trying to reconstruct the data, you have to code those pixels so that you can reconstruct them. But if you're just looking for things that are spatially or temporally coherent, and they're not, you can just ignore them. So Becker and Hinton introduced a way of extracting spatially coherent properties. The idea is to maximize the explicit mutual information between the representations extracted from two non-overlapping patches of the input. If A and B are scalar variables that we've extracted from the two patches, the mutual information between A and B, one way of expressing it, is the log of the variance of the difference between A and B minus the log of the variance of the sum. So what that says is you'd like A and B to vary a lot and to be very different on different training cases, but on the same training case, you'd like A and B to be very similar. So that variance of A minus B is the variance of A minus B on a given training case compared with the variance of A plus B over training cases. If the A and B are vectors, you can just generalize that. So it generalizes to the log of the determinant of the covariance matrix of A minus B minus the log of the determinant of the covariance matrix of A plus B. So we tried this on a simple example that was motivated by randoms.stereograms, which were invented by Euler. So you take an image and you just fill it with random dots, so it has no structure. And then you take another image and you make it just be a shifted version of the first image, a horizontally shifted version. So the only structure in the image pair is the shift between the two images. Now, we were using very small computers a long time ago, so we just took a one-dimensional strip from the left image and a one-dimensional strip from the right image, and we scattered random dots on the left image, and then we looked at the right image, which is a translated version of the left image, and you can see that if you look at two neighboring patches of the image, then they have the same disparity. The offset between left and right strips is the same. So if you train a neural network that looks at the left-hand patch to extract a variable, and you train a copy of that neural network to look at the right-hand patch and extract a variable, the only spatially coherent property is disparity, so that's what they have to extract. And indeed, that works. We got it to work on that simple case, and also on a number of more complicated cases, where it deals with curved surfaces and discontinuities in the surfaces and so on. But there's a very nasty problem with that way of getting things to agree by maximizing mutual information. It's making the assumption that the variables are Gaussian distributed, and that assumption doesn't cause much problem if you're only learning a linear mapping, if you're optimizing a linear function. But as soon as you optimize a nonlinear function, it causes bad things to happen. Those problems are most easily visualized by looking at another method that does the same thing. So I'm going to spend some time describing this other method. So local linear embedding, which was published by Saul and Royce in Science in 2000 and has lots of citations, displays high-dimensional data in a two-dimensional map. It forces points that are close together in high D to be close to each other in the map, and it prevents the whole map from collapsing by enforcing a global covariance constraint. It says that the covariance of all the map points should be the identity matrix. In other words, they have to be spread out. Now, when you do that, that global constraint that the covariance ought to be the identity matrix, it sounds innocuous. It sounds like it would just spread the data out, but it does terrible things. And it's getting over those terrible things that will be the main content of the rest of this talk. So if you look at the representations produced by LLE, that is, the locations where it puts images of digits in a 2D map, the 2D map looks like this, where the colors are the classes of the digits. And you'll see that it has not found the natural classes. In fact, you'll see it's done weird things. Like you've got long strings of data that are basically one-dimensional rather than two-dimensional. They're almost one-dimensional. And these long strings are almost orthogonal to one another. It's not at all what we wanted it to do. It's doing something else. And it's doing that other thing because it's cheating on that identity covariance constraint. It's achieving the constraint by using a method that we didn't intend. So here's what's happened if you use a method that doesn't cheat. This is a method called tsne that's based on a method called SNE, and SNE is based on trying to fix what was wrong with LLE. And you can see there's enough information in the input intensities of the digits to find the natural clusters. So the colors here correspond to different digit classes, and you can see that it finds pretty good clusters. So what went wrong with LLE? Well, it's that global covariance constraint can be achieved whilst not really achieving what you wanted it for. And to explain that, I'm going to go back to a technique that came before SNE and was motivated by LLE, and it's called linear relational embedding. It was work done by Alberto Pacanaro and me in 2000 or 2001. And it's the first place I know where people used a contrastive loss to stop things from collapsing. So what we were trying to do is produce embeddings for vectors and embeddings for matrices so that we could use vectors and matrices to model relational data. We would have a bunch of relational facts like the mother of John is Victoria. And what we wanted to do was learn a vector J to represent John, and a vector V to represent Victoria, and a matrix M to represent mother of, so that when we multiplied mother of by John to get MJ, we would get a vector that was close to Victoria and far from all the other vectors. So we want MJ to be closer to V than to the vectors representing other objects. Our objective function looks like this. The first term says the vector that we get when we multiply J by M should be similar to the vector for V. And we're measuring the squared distance between them. The second term says that for all vectors, in particular all other vectors K, the vector that we get for MJ should be far away from K. And the thing about expressing it like that is, it's no good just making one of the vectors be very far away. As soon as one of the vectors K is very far away from MJ, that squared term will be very big. And because it's e to the minus that squared term, the overall term will be practically zero. So it won't really contribute to that sum. And there's no point making K any further away from MJ. What you need to do is take the Ks that are close to MJ and make those further away. They're the real competition. So what the second term does is try to push the wrong answers away, but only those wrong answers that are close. And that's much better than this global covariance constraint. The global covariance constraint would be perfectly happy if you made one wrong answer a very big distance away. And that's what's causing those one-dimensional strings to be strung out. Now, it turns out that linear relational embedding and its cost function can be turned into stochastic neighbor embedding. So this is work I did with Sam Roweis to overcome the problems of local linear embedding. And the way you turn linear relational embedding into stochastic neighbor embedding is to say there only is one relation. There's only one matrix. It's the identity matrix. And all we want to do is make one vector similar to another vector. But I'm going to tell you which other vectors each vector should be similar to. So what I'm going to do is take some high-dimensional data, and I'm going to look at the distances between pairs of data points. I'm going to say that data points that are close together are similar, but I'm going to measure that similarity by e to the minus the squared distance between the data points. And so I'm going to turn proximity into probability. And then I'm going to throw away the data, and I'm just going to hang on to those probabilities. And now I'm going to try and find how to arrange points in a map, so low-dimensional points like yi, rather than the high-dimensional point xi, so that when I use that same function, e to the minus the squared distance, in the low-dimensional map, I can model the similarities that I found in the high-dimensional data. I'll show you a picture of that in a minute. So we're learning the 2D locations of the map points so that the probability that one of the map points would pick one of the other map points if it was asked to pick a neighbor in the 2D space matches the probabilities if you asked one of the high-dimensional data points to pick a neighbor, and it picked in proportion to how close things were. So here's a picture of it. In the high-dimensional space, you might have a data point I, and we're going to compute the probability that it will pick each of its possible neighbors. And we're going to say that probability is proportional to e to the minus the squared distance, which is equivalent to saying the probability is proportional to the density of that other point, like k or j, under a Gaussian centered at I. So that's how we get the high-dimensional probabilities that I would pick j. And then we're going to try and arrange the low-dimensional points to model that. So the high-dimensional probabilities are just this contrastive function. If you take logs of that, you'll get the contrastive function I gave you before. To get the log probability. And once we've got those high-dimensional probabilities, we then throw all the data away. Or maybe someone just gave us probabilities in the first place. Maybe if they gave us the probabilities of two words co-occurring in a sentence, that would do instead of the high-dimensional data. And then we move points about in a low-dimensional space. So we're going to move the point I around, and the point k around, and the point j around. In order to get probabilities like q, the probability that I would pick j as its neighbor, if I picks a neighbor in this low-dimensional space, using the density under a Gaussian in the low-dimensional space, and we want the qji's to model the pji's. We want the probabilities that we get from the low-dimensional map to model the probabilities we had in the high-dimensional space. And so our cost is the sum over all the data points of the Kullback-Leibler divergence between the probability of picking neighbors that you get for point I in the high-dimensional space, that's p, and the probability that you get in the low-dimensional space. And that can be expanded out. And it turns out, to minimize that cost, what you want to do is, if Pij is high in the high-dimensional space, if they're close together, it's important to have them close together in the low-dimensional space. If they're far apart in the high-dimensional space, so Pij is very small, you can have them very far apart or quite far apart in the low-dimensional space. It doesn't really matter much. Okay. So widely separated points in high D have a mild preference for being widely separated in low D. But as soon as they're fairly separated, separating them more doesn't matter much. And this is very different from using that global covariance constraint that LLE used. So that's what SNE produces, stochastic neighbor embedding, if you try and get it to embed the digits from 0 to 4 based on the Euclidean distances between their images. And it produces quite a good embedding that gets the natural clusters, but it doesn't really get gaps between them. There's one very amusing thing it did, which I'll show you. I took this as evidence that God was in favor of SNE. If you look there, on the borderline between 2s and 3s, it's put 2.5. Okay. Now, T-SNE is just a version of stochastic neighbor embedding where you use a T distribution in the low-dimensional space instead of a Gaussian distribution. And what that does is allows you to get bigger gaps between the clusters. So it creates more room in the 2D, which compensates for the lower dimensionality of 2D. There's not as much room in 2D as in high-dimensional space. That allows gaps between clusters, and so just to remind you, this has nice gaps between clusters, whereas SNE itself doesn't. Okay. So I want to talk a bit more about why the covariance constraint doesn't work when we optimize a nonlinear function. A linear mapping can't change the ratio between entropy and variance. It can't change how Gaussian the distribution is. So if I want to optimize a linear mapping to maximize entropy, I can simply maximize variance. For a multidimensional thing, I can maximize the log of the determinant of the covariance. But that goes hopelessly wrong for nonlinear mappings. A nonlinear mapping can generate a distribution that has two widely separated but extremely tight clusters. That distribution has an entropy of about 1 bit, but it's got high variance. So as soon as you go for nonlinear mappings, you completely decouple entropy from variance. Similarly, if you have two one-dimensional strings of points that form a cross, you can have a high 2D covariance, but very low entropy. And that's what you saw in LLE. And that's why you will never have nonlinear versions of canonical correlation analysis or linear discriminant analysis. Both of those methods are maximizing variance in order to maximize entropy. And you can use variance as a stand-in for entropy if you're only learning linear mappings. But as soon as you learn a nonlinear mapping, the two get decoupled. And that was why the work I did with Sue Becker didn't work nearly as well as we hoped. It kept going wrong because of this decoupling between entropy and variance. Now, people have published papers about nonlinear correlation, canonical correlation analysis, or nonlinear linear discriminant analysis. And basically, they're not really doing nonlinear canonical correlation analysis. They're applying a nonlinear transformation to the data and then doing linear canonical correlation analysis. Okay, so Russell and Saipudinov and I tried using these contrastive loss with the kind of approach that Sue Becker and I were using to extract representations. And it worked, but not very well. And that was because computers were slow. And regretfully, we didn't publish anything, which was entirely our fault. So other people later on rediscovered the idea, and they used contrastive losses to discover representations that were coherent across space or time. In this case, it was time. And they got very impressive results. And I'm going to finish by showing you some work done in my lab that uses the contrastive loss that originally came from the work by Alberto Pacanara and I, but it didn't really come from there because we didn't make a big song and dance about it. We used it for TSNE, but we didn't manage to convince the community that was the loss to use. And so the community had to reinvent it for itself in 2018. So we can't really take credit for it. I guess we would if we were Schmidt-Hooper, but we're not. So this loss is now very popular, and it can be used to get very good representations using unsupervised learning. So I'm going to finish by talking about something called SimClear, developed by Ting Chen in my lab. He showed that you can extract representations from patches of images that are very good representations of what's going on in the whole image, but it requires huge amounts of computation, so it couldn't have been done until very recently. The way SimClear works is it takes an image X, it then does two different crops of the image, Xi and Xj. It then applies a deep net, the kind of residual convolutional neural net used for image classification, to get a representation H. All of this is so far unsupervised. Hi for one crop and Hj for the other crop. It then applies another transformation to the representation to get a vector, and it tries to, which I'll call an embedding vector, and it tries to make those embedding vectors agree in the contrastive sense. That is, within each mini batch, it tries to make the embedding vectors for crops of images that come from the same image agree, that is, be similar, and it tries to make embedding vectors that come from crops of different images disagree, but disagree in that contrastive sense. So if they already disagree a lot, it doesn't worry. But if they agree a lot and they come from different images, it tries to make them more different. And that's what stops things collapsing. One thing Ting discovered is that's not sufficient. If you just take two different crops of the same image, you can normally tell they come from the same image because they have the same color histograms. And so the first thing SimClear will do is learn to extract the color histogram. And if you want it to do something better than that, what you have to do is mess up the colors in in a different way in each of the crops. And then it can't use the color histogram and it will discover something more interesting. So Ting discovered he could get very good representations from SimClear. You do unsupervised learning this way, and then you train a linear classifier on top of the representation. That is the layer before the end here. That was another thing Ting discovered made it work much better. And what you get is very good unsupervised learning. So what I'm showing you here is how well SimClear works compared with other methods from 6 months ago. And the way you evaluate them is you take the representations that they learn unsupervised, and then you apply a linear classifier on ImageNet to see how well you do. And SimClear does better than the other methods. Since then, the other methods have improved, but SimClear has also improved. And what you notice is that if you use a big SimClear net, it extracts representations that are as good as the representations learned in 2012 by the AlexNet, that made a big revolution by showing supervised learning on ImageNet can do very good classification. So simply applying a linear classifier, just one layer of weights, to the unsupervised representations extracted by SimClear does as well as supervised learning. But you have to use a deeper net and you have to use more parameters. Alternatively, you can take the representation extracted unsupervised by SimClear, and then you can fine-tune the whole net, but on only 1% of the labels. And now SimClear again does as well as the 2012 AlexNet. So basically what's happened in the 8 years since 2012 is by using much more computation and much bigger nets, much deeper nets and much wider nets, we can now get the same performance with only 1% of the data labels. And that's because we can do effective unsupervised learning. Okay. I was going to say more things, but I've run out of time, so I will leave it there. That's the end of my talk.
Thank you.
I'm going to try and unshare my screen now.
Visionary talk. And now it's a Q&A time. The first question from Torsten. Professor Torsten, could you? Yeah.
Yeah, thank you. That was a fascinating talk. Many of the techniques that you talked about would be extremely useful in recommender systems. For example, recommender system for this conference that would learn about the semantic relationships between the papers and the interests of the authors and participants. But typically, these systems also have additional constraints like policy rules, for example, that we want to feature student papers at this conference. Or if you go to company settings, there may be business policies. Now, one could, of course, have second stages that would take care of these policies. But can you think of, or do you envision that it would at some point be possible to just have a kind of end-to-end deep network solution where you could feed the policies as well as the data? So feed additional rules that would be fulfilled as well.
I think that should be possible. But what you're going to have to do is you're going to have to put your policies into the objective function that gets optimized. And typically what happens when you do that is you discover that what you thought was your policy wasn't actually your policy. And you discover that by seeing weird counterexamples. And so it's an iterative process. You try and formalize your policy as we want to recommend things, but we want to preferentially recommend things by students. And so you give some preferential weight to a student. And then you discover that, well, actually, no, there's this very well-known student. And now all the things you recommend are by this well-known student. So you didn't really mean that. What you meant was you want to recommend things preferentially recommend things by students who aren't already well-known. But as long as you're willing to go through all those cycles of gradually refining what your policy really is, which you don't actually know until you see things, because we think we can make rules about what our policies are, but you then see counterexamples and you have to refine them. As long as you're willing to do that, which is where a lot of work is, then I think you could make end-to-end recommender systems that do that, yes.
Thank you.
Okay, the next question, Professor Ai-Jun An, could you please ask your question?
Let's go on to another question and come back to him when he's figured.
Okay. So here is one question, by text from Professor Han Barst. She raised this question through text. His question to Professor Hinton is, why do you believe that the brain does not learn via backpropagation?
Okay. Yes, I over many years, I keep changing my beliefs about this. So to begin with, I thought probably it doesn't, because it's hard to see how it could get the information to come back through many layers in real time. So when you're doing perception, you need to pipeline things, right? Video is coming in, and you can't just stop and go backwards to get derivatives. You need to deal with things in real time. So that's one argument against doing backpropagation. I don't really believe the arguments neuroscientists come up with, which say it's sort of impossible for the brain to do. If the brain needed to do it, it could do it. But I think there are alternatives. And more recently, then I went through a period of thinking the brain must do backpropagation, because that's the right way to learn early feature detectors. And then when work from Google and from OpenAI started producing really powerful language models, like the really big models from Google and GPT-3 from OpenAI, I became suspicious, because those language models use very few parameters. Like the language model from OpenAI only uses 175 billion parameters. Now you might think 175 billion is a lot, but that's only about 1/5 of a cc of brain tissue. And with 1/5 of a cc of brain tissue, it seems to be able to learn a huge amount of information. Another way of saying it is the GPT-3 model would show up as just a few voxels in a brain scan. And I don't believe just a few voxels have all that information in them. So I think backpropagation, running for 1,000 petaflop days, is actually a more effective algorithm than the brain's got. I think the brain does have a way of getting information back through many layers, but maybe it doesn't do it in real time, and maybe it's not as effective as backpropagation. So that's what I currently believe. And in fact, at the end of this week, I'm going to give a talk at the Cognitive Science Conference, which is very similar to the talk I gave here, but has it has less detail than I gave here. But in the last part of it, I briefly outline how I think the brain might be able to do something other than backpropagation. And I'll leave it at that.
There's some question from the audience. Maybe you can read it.
Yeah, one more question from Kevin. The question is, NLP models are trained by text corpus. The question is, Professor Hinton, do you think we can train NLP models by vision? I think the question is,
I have two people who work in my lab called Jamie Kiros and William Chan, and they kindly put my name on a paper, which I didn't have much to do with, which is learning better representations for words by also using vision. So their idea was take the word and do image search, and then try and find embedding in Google, and then try and find embeddings that are good for both the typical image for that word and the text that contains that word. And they showed that they could get slightly better embeddings that way. The system was called Picture Book. And yes, I believe that it's very impressive what GPT-3 can do, but I think it would be able to do even better if it was hearing sentences describing scenes that it was seeing. And more recently, the same technique, or very similar techniques, have been applied to images, and they're very good now at completing images. Instead of you giving them some text and then giving you the next bit of text, you can give them part of an image and they will fill in the rest of the image. And it's extremely impressive what it does. And so clearly it can do both. It can learn to do both images and text combined. And that ought to be better for learning what's really going on. It's amazing you can learn anything from just text by itself.
Okay.
Yeah, I found one question from audience too. It's a bit long. Should I read it or you read it? Okay, I read it.
Okay.
Yeah, Professor Hinton, do you think, the audience asked, do you think that IR problems are more subjective, such as people can have different opinions about IR systems result, then they can have judging the content of an image or the translation of a sentence, so that there isn't much progress of the deep neural networks in this area compared to the NLP and the computer vision?
Okay, so I sort of have two things to say about that. The first thing is, if you do good work in one area, like how to get neural networks to learn things, particularly if you win an award, people then think you're an expert on everything. And I'm not an expert on IR. So I was slightly embarrassed to be talking to this conference because I don't really know that much about IR. So you shouldn't believe my opinion too much. My primitive view about IR is that if you want to retrieve information from documents, you really ought to understand what's in the document. So there's all sorts of tricks at looking at frequencies, particularly frequencies of rare words in documents, and you can do quite well, surprisingly well with that. And then you can use kind of bag of words models. But it's clear that if you really want to do good information retrieval, you have to understand what's in the document. My fundamental belief is that neural nets are going to lead us to be able to understand what's in documents, and that's going to lead to much more sophisticated information retrieval. So although I don't know much about IR, it seems to me I'd like to be able to ask a question like, find me a document in which Mike Pence says something that's clearly false, and he says it because of his religious beliefs. Now, you can look at a document that says something about religion and something about Mike Pence and something about false, but unless you understand what's going on in the document, you're not going to be able to produce just the right answers to that. But I'll leave it at that because I'm not an expert on information retrieval.
Okay, Professor Hinton, the last not the least question. So one question is, what is your idea? How can we incorporate causality into the deep learning framework?
Yes, I've had this debate for a very long time with Judea Pearl, and I think his work is very important, and I think causality is very important. But I think it's a higher level thing. So my basic approach to it is there's the sort of basic mechanisms for learning in these neural networks, for learning big distributed representations. And then there's higher level structure that emerges, like building causal models. And I don't believe that causality is going to be a very low level thing in these nets. I think we're going to get nets that are good at finding structure in data. And that causal models of the kind that people interested in graphical models like to produce are much higher level constructs. They'll be implemented in neural nets, but I think it's a mistake to think that the neural nets themselves are going to look like the causal models. I think they're going to implement causal models at a higher level. Okay.
Okay. Thank you very much. I noticed there new questions keep coming, but it's running out of time. So let's thank Professor Hinton again for his very visionary talk and question answering session. Thank you very much.
Thank you.
Thank you.
Thank you.